fugacity goes to pressure. In other words, in fugacity versus pressure plot, I would have a straight line of slope 1. Look at what happens here. Unfortunately, I didn't use quite the same scale. 0.5 would be here. But you can see at 0.5 fugacity, what is the pressure? It's right at about 0.5. It starts with a straight line, tangent line of slope 1.
Can you repeat that?
One. Within limits, come on. I was talking.
I was asking a question.
Yes, one, but we have a class of 50 people. So, anyway, as pressure goes to 0, fugacity goes to pressure, which means fugacity against pressure plot would be a straight line with slope 1. F equals P is a straight line of slope 1, which means at these regions, if you read at any pressure fugacity, it's about the same number. Okay? Then you can see curvature. So clearly low pressure is where we have gas. You see curvature. You see a second line on top. That's for the liquid phase. As I'll show you in a minute, or shortly after, so the interval, minimum equality of Gibbs free energies means equality of fugacity. Actually, we can see. Okay. This is the relationship between Gibbs free energy and fugacity. We know we must have two phases in equilibrium equal G. G ideal gas is independent of phase. It's ideal gas phase at that temperature and pressure. So I'm subtracting the same thing. We also know that in equilibrium we must have equality of temperature between phases. Okay? So that means the departure, the scaled departure Gibbs energy of the vapor phase must equal the scaled departure energy of the liquid phase. If I have two phases in equilibrium, not only G's must be equal, but the scaled departure G's must be equal. Subtracting the same number doesn't change the minimum. Dividing by the same number doesn't change inequality. Which means fugacity coefficients must be the same. And since also pressure must be the same when I have two phases in equilibrium, that means fugacity must be the same. And minimum Gibbs energy translates into minimum fugacity. So we can be using equilibria replacing G with fugacity. When we have two phases in equilibrium, we have equality of fugacities, and when we have the possibility of two phases, minimum Gibbs energy wins, which means minimum fugacity wins. The intersection is where the vapor pressure, when they're equal. Equal fugacities means vapor-liquid equilibrium. So this is the vapor pressure, and this is the fugacity at the vapor pressure. Here, fugacity of the vapor is lower than fugacity of the liquid. That means that we have vapor phase. To the right of the vapor pressure, you can see that the liquid fugacity is lower than the vapor. This graph will also be very helpful in helping us calculate fugacities and approximate fugacities. One thing you see from this graph is a very rough approximation of fugacity for a vapor would be what? The pressure, right? But as you approach vapor pressure, you have curvature. As we will see, when we calculate fugacity of a liquid, the roughest approximation will be fugacity of the liquid is the vapor pressure at that temperature. Approximate the liquid fugacity curve has a relatively small slope. Depends on the substance, but for many substances, and here I'm going with many pressures here, okay? These are megapascals. the units. So this is not a very big stroke that you see on the liquid side. So the roughest approximation of fugacity of the liquid is going to be vapor pressure at that temperature. We'll do all that, if not today, very soon. But do you get an idea of this? Now, what are meanings of fugacity? You can attribute several physical meanings. Clearly, it has the units of pressure. Some people view it as a corrected or as an adjusted pressure. You can give the interpretation, it's the pressure that the fluid would have if it had G, ideal gas, equal to the G it actually, if it was an ideal gas with the G, with the actual G instead of having the G ideal gas. You can see from this, from the cover the definition, but if if it was an ideal gas, not with the actual G ideal gas, but having the G of the real fluid, that term would become 1, and then you have fugacity equals pressure. So from that point of view, you can view it as the pressure that the fluid would have if it was behaving as ideal gas with the G of the real fluid. Another explanation you can give, which is popular, is the tendency to escape from the phase it is in. What must you have at equilibrium? Which phase wins out? The phase with the lowest fugacity, okay, minimum fugacity. So, the higher the fugacity, the less you want to be in that phase. Okay? So from that point of view, you can consider fugacity as the tendency to escape from the phase you're in. The fugacity of the vapor will be the tendency of the vapor to escape the vapor phase and enter the liquid phase. The fugacity of the liquid will be the tendency to escape the liquid phase and enter the vapor phase. When we have a tide, we have equilibrium. Okay? Yes?
By that second definition, does that mean like the substance is always trying to get back to equilibrium in phases?
I don't know how. From that definition, everything, molecules behave, collide and settle, and there's a tendency for a liquid to go up on vapor, right? There's always. So from that point of view, fugacity can be explained as a tendency to escape from that particular phase. I don't know that. It's not the easiest concept to understand, but it's really a mathematical invention to overcome the infinity that we have with Gibbs energy as P goes down. But if you want a physical explanation, either with adjusted pressure or tendency to escape this. Okay. I mentioned that there are alternative definitions of fugacity, and probably the most common one so this is the definition I like, okay? That's the one I'm saying, and I'm curious, USF students, probably your text will have the alternative definition. If any one of you has the text that you used before, I'm curious to see what definition they have, but alternative definition So here is defined in terms of a ratio of the fugacity given temperature and pressure and the fugacity at the same temperature but the reference pressure. So P naught is a reference pressure. Yes, please.
What's it say in the parentheses again?
Hmm?
What does it say in the parentheses again?
Which parentheses? I have a lot of parentheses. Oh, this?
Yeah.
That's the name of the author of the text that was used in the spring semester.
Oh.
Okay. It's a great name. Panagiotopoulos. Now say it fast. All right. Let me show you that this definition, this expression, can be obtained from the Sandler definition, but the reverse is not true. But, so we have this definition, and this is at same temperature, two different pressures. So let's see with the definition, and I'll use the one with the integral v minus RT over P dP. Let's first of all calculate what is the ratio of fugacities at two different pressures. So fugacity, let's say at pressure P2, comma T, over fugacity at P1, comma T, is going to be equal to P2 let me save a little bit of pore space over P1 e to this P2 on the top divided by e to this P1, but you know dividing is the same as multiplying e to the minus. So I can combine the ratio of the e parts, and t is the same, so can be factored out in front. E1 over RT, the integral at P2 Okay, everybody understands? It's P2 times this divided by P1 e to the this, but 1 over e to the a is e to the minus a. So instead of writing the division e down here, I wrote on the top e to the minus, and I had e to the b divided by e to the a. That's e to the b times e to the minus a, or e to the b minus a. Okay? And because the RT is the same in both the b and the a, I took the RT as a common factor. Calvin, how do you do? Clear? Okay. Eric is not here, right? I forgot the names of the USF students. So. Oh, there you go. Sorry, Eric. You're hiding behind. Oh. I just raised the thing I didn't want to do. Okay. All right, let's continue. So, I can rewrite that as P2 over P1, and let me write it again. Okay. The first parts are the same, and just realized something.
Looks good.
Just realized the problem. But I in my notes on what I have done. Okay, let's leave it as 1 over RT integral T P equals 0 dP2 dP. This is the first part. And the second part, T is constant, you can take it out, and you have only P here. Since I have only P, I can combine the two. I don't have T is the same. Yeah. Oh, okay, T is the same. I have a question about something I did if it's going to be right, but anyway, times e to the, definitely what I'm doing now is correct so far. So the second part, I have 1 over RT, and I have integral, there is, okay, 1 over RT, the T is the same in both of them. Yeah, the T is the same. Okay, I think. So you can pull the T out if you want, the R out, so RT would, this RT and this RT both factor out, and I can cancel them. And then because I have integral 0 to P2 minus integral 0 to P1 becomes integral P1 to P2 of, there's a minus dP over D. Okay. And this is, of course, ln P2 over P1 with a minus in front. So this is e to the minus ln P2 over P1, which is the same as e to the ln P1 over P2. Okay? Minus ln is ln 1 over a. So far so good, Christian?
Why do we take the rate? Why are we taking the ratio of this function?
You following what I'm doing? Everybody okay? Why is a different question? Okay? I'm going to derive this definition. That's what I'm telling you. I'm going to derive that definition. So, everybody okay with this? So what's that? That's P1 over P2. Okay. What happens to P1 over P2 times P2 over P1? Becomes 1, right? Okay. So, this is equal to E 1 over RT integral T equals 0 to Tp2 dP minus integral T equals 0 dP1. Oh yes, because T is constant I can do that. Because T is the same,